Hi, I'm Jay Uri from University of Georgia. Today, I'm going to introduce my work on scalable differentially private deep learning framework. This is a joint work with Daniel Kiefer at Penn State University. In this work, we are going to consider training a neural network on the privacy constraint. Although there exists many algorithms you can use to train a neural network, in practice, one typically uses stochastic gradient descent and a backpropagation algorithm. The backpropagation algorithm consists of two phases. During the fourth step, we pass the input through the network to obtain the output. The loss function L defines the error of our neural network F, which is the difference between the output of the neural network and the ground truth. During the backward step, this error information is propagated back through the network from the top to bottom, layer by layer. Using the gradient calculated by this backpropagation algorithm, we can update the parameter of our neural network. In this work, we are going to assume our input data set D contains some sensitive information, for example, medical records or insurance claims. The specific notion of privacy that we will be using in this project is differential privacy. Differential privacy is a mathematically rigorous notion of privacy that provides strong privacy protection against the adversaries with background knowledge. Before we define differential privacy, we first need to define neighboring data sets. We say two data sets, D1 and D2, are neighboring if they are exactly the same except one individual's record. For example, as shown in the figure, the one with Alice and one without Alice record. Differential privacy enforces that the output distribution of the algorithm M over two neighboring datasets, D1 and D2, are indistinguishable to the adversary. Given the output of the algorithm, the adversary cannot distinguish the D1 from D2, and hence the presence or absence of Alice is hidden to the adversary. There also exist other variants of differential privacy, for example, the moment accountant or zero concentrated differential privacy and Renyi differential privacy. In this work, we use the Renyi differential privacy to trace the privacy loss during the training. This divergence-based definition of differential privacy ensures that the output distribution of our algorithm M over two neighboring data sets, D and D prime, are close to each other, and it measures the distance between these two distributions using the divergence measures. And this is expressed as the constraint of the moments of privacy loss random variable. An important concept in differential privacy is the sensitivity. Sensitivity of a creative function Q is defined as the largest difference of function outputs between two neighboring data sets. Intuitively, this sensitivity measures how much difference one individual can make on the output of a function. In our context, it measures how much influence one individual can have on the gradient. Okay, so we are going to look at the details of neural network training steps. First, we sample a mini batch of size B from the input data set. For each example in the mini batch, we compute the per example gradient, and we take the summation or average to obtain an aggregate gradient. Once we have this aggregate gradient, then using this gradient descent update equation, we can update the parameter of our neural network. Now, we turn our attention into the differentially private neural network training. As before, we start by sampling a mini batch from the input data set. And for each example in our mini batch, we compute the per example gradient. Once the per example gradients are calculated, then we inspect the norm of each gradient. If the norm is greater than the predefined clipping threshold C, then we clip the magnitude of the gradient. If the norm is smaller than C, then we use it as it is. After clipping the gradients, we take the sum of those clipped gradients and add Gaussian noise to satisfy differential privacy. We call this aggregated noisy gradient a private gradient. Once we have this private gradient, then we can update the parameters of our neural network. Okay, so what is the challenge in implementing this gradient clipping method? As we have seen before, training a neural network under differential privacy requires accessing per example gradient and modify the per example gradient depending on their magnitude. However, existing deep learning framework, they are tailored to the calculation of the aggregate gradient, and they don't provide an easy access to the per example gradient. So there exists a naive way to implement this gradient clipping using the existing deep learning framework. Given a mini batch of examples, we take one example and then backpropagate through the computational graph, which will give us per example gradient. We repeat this process for all observations in our mini batch. While this allows us to implement the gradient clipping without making any modification to the existing deep learning framework, this process is extremely slow because we have to backpropagate for all observations in our mini batch. Now the question is whether we can do better than this or not. To get an idea, we take an example of fully connected network. We are going to inspect the mathematical derivation of calculating the per example gradient for linear layers. We denote the pre-activation by Z, and we use small letter a to denote the activation of the layer. Here, the Greek letter phi corresponds to the element-wise activation function. Given this notation, let's look into more details. Using the chain rule, we can express the derivative of our loss function L with respect to parameter W as the product of the two terms, in which the first term is the gradient with respect to pre-activation, and the second term is the derivative of pre-activation with respect to parameter W. And it turns out that the second term is nothing but input to the layer. Combining all of this, we see that the gradient of L with respect to parameter W can be expressed as the outer product between two objects. The first object is the gradient with respect to pre-activation, and the second object is input to the gradient. Let's take another example. The second example is the convolutional layer. The convolution is also a linear operation, and similarly, we denote the pre-activation by Z, and W denotes the kernel, and X denotes the input image. Here, the star symbol corresponds to element-wise product between two tensors. Again, using the chain rule, we can decompose the gradient of L with respect to W as the product of two terms. The gradient with respect to pre-activation and the derivative of pre-activation with respect to parameter. After applying simple calculus and manipulating the terms, we observe that the results can be expressed as the inner product between two tensors, where the first tensor is the gradient of L with respect to pre-activation Z, and the second term is the input to the gradient. Recall that we obtained the similar results for the linear layer. The per example gradient was expressed as the results of performing an operation between the gradient with respect to pre-activation and input to the layer. The only difference is that for linear layer, we have to take the outer product, while in here, we take tensor inner product. Actually, this is not a coincidence. We can generalize this observation to other types of the layers. In this table, we present the per example gradient for different types of the layers. If you look at the third column, they all correspond to the gradient with respect to pre-activation, and the second operand is always input to the layer. And depending on the layer type, we just perform different type of the operation between these two operands. Okay, how can you implement this? Our observation is this. In order to calculate the per example gradient, all we need is the gradient with respect to pre-activation and input to the gradient. To implement this, we create a wrapper classes for different types of the layers. During the fourth step, we store the input to the layer, and during the backpropagation step, the gradient with respect to pre-activation is calculated by auto-differentiation library, and it will be available to us. Once we have this gradient with respect to pre-activation, we can calculate per example gradient. We make another observation. So let's define nu sub I as the minimum between these two values. And once we define the nu in this way, then the clipped gradient can be expressed as the weighted sum of per example gradient. And in turn, we observe that this weighted gradient is the gradient of reweighted objective function, L. That means once we have calculated this weights for each example, then using the existing deep learning framework, we can calculate the clipped gradient. This allows us to use the efficient implementation of existing deep learning library to calculate the per example gradient for differential privacy. Here we compare the performance. Here we compare the performance of our proposed method against the baseline algorithms on different neural network architectures and on different data sets. So we consider multi-layer perceptron, convolutional neural network, LSTM, and transformer network. For data sets, we use MNIST, Fashion MNIST, CIFAR-10, and ELSON, and IMDb movie review data sets. Here are the baselines we consider in our experiments. Non-private is the non-private method, and NXBP is the naive implementation of gradient clipping, which requires backpropagating multiple times. Reweighted GP is our proposed method, and multi-loss is the existing method that defines the multiple loss functions and asks the auto-differentiation library to calculate the gradient over all those loss functions. Here we present the results of comparing our method to other existing method. So y-axis represent per epoch processing time, and x-axis correspond to different type of neural network architecture. Notice that the y-axis in log scale. As you can see, our proposed method greatly outperforms the existing method, especially on very complex neural network architecture, such as the transformer network. The gap between the proposed method and naive implementation is larger. Here we compare the per epoch processing time on varying batch sizes. As you can see, as we increase the mini batch size, the per epoch processing time decreases. This is due to the fact that our proposed method can utilize the GPU parallelism. Here's the results on different depths. So as we expected, as the depth of the network increases, the processing time increases. The rate of increase for our method is similar to that for non-private method. Here we present the performance comparison on larger network, for example, the ResNet and VZZ network. We note that for larger input image size, the existing method, for example, the multi-loss method, fails to run on ResNet 101. Since VZZ network requires huge amount of memory and multi-loss method fail to run on this neural network architecture. So in this work, we presented a scalable method to calculate the per example gradient for differential privacy. And we empirically showed that our proposed reweighted GP method greatly improves the scalability of differentially private deep learning. There also exists a limitation. Our proposed method is not compatible with batch normalization layer. So whenever we have batch normalization layer, we will have to replace that with other types of normalization method. For example, layer normalization. Okay, thanks for your attention. And if you have a question, feel free to ask me. Thank you.